So let's look at arc length first. So first, do you know your conversions from degrees to radians?
It's like the number over 180 times pi.
Yep. So for example, like let's give 90 degrees for example. 90 out of 360. Just so we know, it's usually going to be 90 divided by 360 is going to give us 1/4 of the entire circle radius. So we know that our radian out of 2 pi is going to be 1/4.
Yeah.
So let's use the arc length formula. 90 times pi over 180 equals 90 pi
Over 180.
over 180, which is going to give us pi over 2. Which makes sense because pi over 2 is 1/4 of 2 pi, which is our entire radius in radians. Now, why this matters for arc length is when you're calculating arc length, sometimes the problems are going to give you radians, sometimes they're going to give you degrees.
Yeah.
So, for example, let's make a clear circle here. Times it's going to go from the center, which is A, B, just labeling our points. It's going to give you 75 degrees. And it's going to ask you, what is the arc length?
75 over 360. Oh, wait, no. No.
Not exactly, because when it gives you in degrees, the central angle is the arc length. So the arc length is just 75 when it gives you in degrees. But sometimes it'll give you radians. Not. What am I saying? This is wrong. Ignore that. Because it won't give you a simple problem like this. I think it'll give you something like this. It'll give you a distance too. Like, for example, 10 inches for the radius. Now, this is where your proportions come in. So you're going to do your central angle, 75 degrees, over 360 is equal to your arc length over 2 pi r. And you just condense. So, for example, 75 over 360.
And this is defined BC.
This is to find the arc length of BC.
So can we just divide 75 over 360 times 2 pi r?
Yeah, pretty much. Let's do that. So, I like to cross multiply actually. That's just a personal thing. You know what? Nah, no, that's not gonna work really well for this. Our R is going to be 10, so this is going to end up to be 20 pi. 20 pi. Now, well, actually, yeah, you're right. So cross multiplying would not be the best for this because you want it to stay proportional. It makes it easier to visualize. So 75 over 360. What I like to do, I just like to take it down number by number. So 75 divided by 5, that's going to give us 15. And 360 divided by 5 is going to give us 60, 72. Pretty sure.
Yeah.
Yep. And from there, can we divide even further? Mm, yeah, we can go even further than that. So we can go 5 over
24.
24 equal to x over 20 over pi. Now that we've simplified, now we can start cross multiplying to make it easier to understand. So, example, our 20 times 5, 20 pi times 5 is going to give us 100 pi equal to
Is equal to
24x.
x.
Now x equals 24 over 100 pi. And that's our arc length.
Yeah.
Now, the second one, you said sector area, correct?
Yeah.
Let's look at sector area. So with sector area, usually they're going to give you something in the form. Instead of giving us our central angle like they did with arc length, they're going to give us our actually, no, this is technically sort of our central angle. They're going to give us our outside angle. Actually, correct. Forgive my mistake. It is our central angle. Our central angle and our outside angle are the same thing. So, going to give us something in the form of n degrees. And they're going to give us something in the form. They're going to give us our radius r. Well, with the area of the sector, our area is going to be equal to n over 360 times pi r squared. The reason for this is our central angle over 360 is going to give us the proportion of how much of the circle is being covered by the area, how much we need to calculate. And now times pi r squared is to find the actual area of how much. This is the proportion.
Proportion of the circle.
Proportion. And this is the actual area. So for example, just a simple one. Let's give you, let's say 60. Our n is 60. And our radius is, let's say 20. Now we would take our 60 over 360 to find our proportion, which equals 1 over 6, and pi r squared, which in this instance is 20 squared, would mean we would have 400 pi times 1 over 6, which we can simplify down to 400 pi over 6, which equals, let's see if I can figure this out, 200 pi over 3. So to start off with congruent chords, the way that you can prove that two chords are going to be congruent is if they are equidistant from the center. That means their midpoint line is going to be equidistant from the center, which would
So the
mean,
same length.
yep. So this length and this length are going to be equal. So for example, they could give you something, oh, apologies for that circle again. Circle O, two chords, they could give you something like 24 equals x 3x. That is a 3x plus 7. And
Is
since
that
you,
the? Oh, that's the length of the other one.
and it would ask you find x,
So 3x plus 7 is equal to 24.
correct. The reason you would find x is in order to prove that these two chords are congruent. So 3x plus 7 equals 24. 3x equals
17.
17. X equals 17 over 3. This is going to be where these two chords are congruent. That's a basic one. Let's look at some other circle theorems while we're here. So while we're on the subject, let's look at perpendicular bisectors. So a theorem for circle theorem. Maybe this congruent chord stuff. So with perpendicular bisectors, a theorem. Let me draw this out. Theorem is that if the diameter or radius is perpendicular to a chord, then it bisects the chord and its arc. So this is going to be our diameter. This is going to be our chord. Let's say let's call this chord X, Y. So again, they would probably ask you something like find the values of if the diameter bisects chord X, Y. Find the value of X, and it's gonna give you something similar, probably like X minus 7, 38, and you just have to set these equal to each other and multiply out, which I think you can do that. So look at some other chord ones. All right, this one's important. Let's look at this one. Now, this chord is that I know it looks a little wonky, but we're gonna break this down. So let's call this chord XY and WZ. So let's fix that W. Now this one, I think this is gonna be our final one. I think um, this theorem states that if two chords are congruent, then corresponding arcs are going to be congruent as well, which means with chord XY and CW, if we could prove congruency with them, their arcs here are going to be
The angles
congruent as well. Yep.
equal.
So again, they would probably ask you this one can get a little bit complex. They could ask you for multiple variable solutions. So for example, uh, let's go. Let's go. These are same variable names, just to not make things confusing. And let's say 3x minus 7, 24, 2x, 2x. Now, they might ask you to solve for multiple things. They might ask you to solve for the length of the chord. And they might also ask you for uh, for the central angle, the corresponding arc degrees, which means we already solved 3x minus 7 equals 24 last time, correct? Gonna be x equals 20. What do we say? So we said 34 over 3. We said, I don't even remember what we said. Let's just say 17 over 2. Now we need to solve for 2x. So 2x equals same thing, 17 over 2 times 2, which cancels out, and we're just left with 17 degrees. So they might just ask you for multiple solutions. Might ask you for the length of the chord along with the central angle as well.